Hey chemistry crew, Mr. Collier here. Today we're going to look at yet another gas law. This is the ideal gas law, and this is your notes on page 20 in your gases packet. So the idea of an ideal gas is one that follows these rules that we've been talking about. It's the best way we have to explain the behavior of real gases, and we'll talk a little bit at the end about what it really means to be an ideal gas and where that kind of breaks apart. So when we're looking at an ideal gas, it follows this general equation, PV equals nRT. Now, what does that mean? What it means is that if you multiply the pressure and the volume, it's going to equal the number of moles you have multiplied by R, which is a gas constant, multiplied by the temperature in Kelvin. Now, let's unpack this because we've actually looked at a lot of this before. Pressure and volume are units that we've used before. Temperature, that's also something we've been using for gases. So really the two things that we haven't looked at yet in this chapter are N, the number of moles, although that certainly is something we've looked at time and time again in chemistry. Now we're just talking about how much gas is there in this container. And that really leaves the only new thing is this R. Well, the nice thing about R is that it is a constant. It is a constant value, meaning it is always just the same number that you plug into an equation to make all of this relationships. It kind of shows what that relationship is. Now, something important about R, and this will come up again when I do the sample problems, is that it has a very fixed unit. It is liters times atmospheres divided by moles times Kelvin. What that means is when you do these problems, those are the units your other variables have to be in. You have to have volume in liters. You have to have pressure in atmospheres, number of moles in moles, and temperature in Kelvin. So that specific set of units is going to be important for all of the problems here. Let's unpack it a little bit more. Again, PV equals nRT by looking at some stuff that we've actually already looked at. Under normal temperatures and pressures, gases behave like this. They follow these rules. And the rules are, again, as we've generally discussed, that the more of a gas you have in a container, right? So as N, the number of moles goes up, the pressure also goes up. And I think that's pretty intuitive if you think about it. More gas in a container gives you more collisions, and more collisions leads to more pressure. So here we have a little picture of that. And again, this is if you're keeping the other variables constant. If temperature doesn't change, if volume doesn't change, then putting more gas in a container is going to increase the pressure in that container. We also have talked about relationships between temperature and pressure. So if you increase the temperature of a gas, you're speeding up the particles, and so the pressure is going to increase. If the particles move faster, you've got more collisions between those particles in the container, and that's what pressure is. And so heating a gas increases the pressure. Again, this is if you keep those other variables constant, if you're not changing the volume, if you're not changing how much gas is in the container. Here's that relationship, pressure and volume. Here we have volume and pressure. This is the only one that is inverse. So if the volume goes down, then the pressure goes up. And so if you have a smaller volume, you've got more collisions. So if you shrink a container, you're going to have less space for those gases to move around in. So they're going to collide with the walls more often, and you're going to have more collisions, more pressure, right? So you got two direct and one inverse. More gas particles, more collisions, more temperature, more collisions, but volume is the opposite, smaller volume, more collisions. And we're really just putting all those together into taking a snapshot of a gas at one particular point in time, PV equals nRT. So how many grams of carbon dioxide occupy a volume of 36.9 milliliters at 158 kilopascals and 72 degrees? So this is the equation we're going to be using here. One of the key ways as you do some of these problems to know that this is the equation you're working with is you're only given a snapshot of the gas. In other words, you're not given two pressures or two volumes or two temperatures. You're just given one of each. And typically you're given more information, right? Here we have all of the variables but one, whereas in most of the other ones, we've only got one or two variables. So now we want to first make sure that all of our units are in the right units for R. So that means that milliliters needs to be in liters. So I'm going to slide the decimal to make it liters. That means that temperature needs to be in Kelvin. So I'm going to add 273. and it means that the pressure needs to be in atmospheres, not kilopascals. So I'm going to convert using my conversion factor to get to atmospheres. Once I have them all in the appropriate units, now it's as simple as plugging them into the equation. P, pressure, 1.56 atmospheres, which I converted, times V, volume, which I converted to liters, equals N, which is what we want to know, how many grams, although as we're going to see, this is going to spit out moles, but that's related. R, this is nice, it's always my 0.0821. This is a number you do not have to memorize, by the way. This is in your reference packet. Notice my units there are going to be all of my standard units for this type of equation, and then multiply that by the temperature again in Kelvin. I start dividing and simplifying this equation. My units start canceling, and I'm going to be left with N, a number of moles. Moles is going to be the only unit that doesn't cancel out from all of this. The one little thing about that is it did not ask me how many moles of carbon dioxide. It asked me how many grams, or it might even ask me in a different problem how many liters. So now I simply need to do a conversion from moles of carbon dioxide to grams of carbon dioxide by multiplying by the molar mass, or the number of grams per mole of carbon dioxide. That will get me the grams of carbon dioxide. This was a lengthier problem because I wanted to show you all the different things we can throw at you. But the basic idea is there, which is pressure, volume, moles, and temperature are related through this ideal gas law equation. So the last thing I want to mention is in your notes on page 21, which is when does this ideal gas law not hold true? So one of the things we said about gases at the very beginning of this chapter is that they individually basically don't take up any space because there's so much space in between the particles, and there's no real attractive forces between them. So if you have very low temperatures and high pressures, then these gases are not going to behave like this, because as you get very, very cold and under a lot of pressure, the actual volume of the particles themselves becomes significant, and so the particles are going to start to behave differently. They're going to be attractive forces, those intermolecular forces in between them, and they become large enough that they start slowing down, and these rules are a little bit different. Now, we're not going to look at the math of when they're different, but I just wanted to point that out. At these extreme circumstances, this PV equals nRT is not quite as true. But using that equation, you should now be able to do packet pages 22 to 25. Check Google Classroom to see which ones were assigned to you. And good luck. Let me know if you have any questions.